Okay, guys, welcome. You have a few minutes, get to know the people around you a little bit better. It's going to help for the lecture, the sample mock lecture that I'm going to give, because I'm going to ask you to think about some things and discuss it with your neighbor anyway. So get a little bit friendlier with your neighbor. I need a little bit of time to set up my, my stuff. Probably will put on my microphone. I use technology when I teach, but technology and I rarely ever get along, so if you hear me cursing under my breath, don't hold it against me, okay? So feel free to talk amongst yourself. I'll get your attention when I need it, okay?
We're just going to get the eye clickers out if that's okay. Yep.
Spread them out. Tell them to work in pairs.
Yep.
Okay, they should be good.
No worries.
Thanks. One thing, folks, listen up. Our volunteers are going to be passing out some clickers. How many of you have used clickers before at your school? Okay, so some of you will know what they are. Basically, they're like a really simplistic TV remote with only 5 channels, well, an on and off button and 5 channels. Really simple to use. We don't have enough for everybody, but this is actually a good thing. So they're going to pass them out to every 2 people, or you can work in groups. Think about the problem, and then the person who's physically holding that eye clicker will respond on behalf of the group, okay? So they're coming around now.
We're going to do it. Just remind them to take notes to the best of their ability. They wanted me to say that.
And then if anyone needs a quick. Okay, folks. Thank you. If anyone needs a booklet, okay, can you hold one up? Hold the booklet up. So you need a booklet. Can you please raise your hand? And one of the volunteers will come around and give you one. You'll need it for this mock lecture because there's a sample of the course notes from Chem 120 in them. I think they're pages starting on, is it page 8, Rick, or 6? 6 or 8? 8. Right, so page 8 are pages from the Chem 120 course notes. So the way Chem 120 is organized, we provide course notes that basically give us the script that we use or the baseline of content that we focus our lectures on. The instructors in Chem 120 will use those course notes in different ways because everybody has their, as Rick mentioned, every instructor has their own teaching style, but the course notes provide the basis of what we will focus on during lectures and ultimately assess you on during tests and exams. We prepare that, you bring them, the expectation is you will bring them with you to class or have them with you. The way I teach, the way Rick teaches, is that you will follow along with us in the course notes. Other instructors might use them differently, but depending on which section you're in, it will become clear. Okay, so you will need them today, so we'll be focusing in there on page 8. Do your best to take some notes. Practice your note taking. Maybe try using some of the tips that Rick talked about. After we're done the lecture, we have some student volunteers who are also taking notes, and they're going to kind of, they will come up at the end and show you what they did, you know, what their strategies are for taking notes during the same lecture that you were in, and we can then talk about and reflect on some different strategies for taking notes in this lecture. Okay, so just do your best. It's not a test. Okay, here's your first test in university. Not official, but let's just see how this goes. Now, the first test is going to be to set the frequency of your clicker properly, okay? I want you to think about this question. I will give you some time to think about this question, and then I'm going to start the clicker or the timer so that you can enter your answers. Rick mentioned a good strategy for lectures is to skim the notes that you have for a course, the lecture slides, the textbook, whatever is appropriate for the course that you have in advance to prime the mind. In my teaching, one of the strategies I use to help prime the mind is to ask questions at the beginning of a lecture, things that will be related to what we're talking about today, to just prime your mind a little bit. You might not know the answers to the questions, but by not knowing the answer, maybe that will help you focus on some key ideas during that lecture. So that's what we're basically simulating right here. Here's the question. I want you to think about these 3 structures down below, 1, 2, and 3. And there's some statements, and you have to figure out or answer which one is incorrect. Okay? So you've had some time, hopefully, while I was blabbing on, doing some other things, that you have started to think about this. When I start the timer, an announcement is going to come up that we have to set the frequency with some, and there will be some instructions for doing that. Once we go through that process, then you'll be able to enter your answers. I'll give you like 3 minutes or so to discuss, okay? We're not in a, we're not in church. You're allowed to talk to your neighbor while the timer's on. You're going to be talking about the problem, not about, what you hope we're serving for lunch, okay, or things like that. Focus on the task at hand. So here are the instructions. It says, if you can't read, you want to hold your power button down until the light flashes. And then once it flashes, press the letter C, followed by the letter A on your remote to set the frequency to CA. That's the frequency for this room so that our clickers aren't interfering with what's going on in other rooms. Okay? So I'm going to find out if people are going to be able to enter their answers, whether this has actually happened. Okay, you can see the timer is going down from 3 minutes. Do your best. Okay, folks, come on. I mean, you can keep talking, but I'm just reminding you of the time. We have just over a minute left, so, you know, it's okay. This is not counting for marks, right or wrong. Give your best guess. There should be 180-ish responses in the end, yeah?
Do you want us to enter our response at the time the time reaches 0? Or
No, anytime, anytime.
Okay, thank you.
You need to enter your response before the time expires. Ten seconds. Okay. So, we'll talk about this question a little bit later. So the things that have come up in this question are words, some key words, things like isomeric structures. We'll come back. It always comes back. Isomeric structures, nothing wants to stay on there. Resonance structures, non-equivalent comes up. This concept of formal charge appears several places. Okay, and making decisions about what structures are better than others. But we're talking about molecular structure. Okay, Rick, and how this thing, I'm trying to be fancy here. I've gone to full screen mode. How can I actually change the thickness of this pen? All right, nice and fat. Let's go with that. Ah, sweet. Okay, so, see, I like to experiment. Teaching's fun for me. I like to just have a very authentic lecture. I make mistakes. Sometimes I say, I make mistakes to see if you're paying attention. No, it's just because I make mistakes. But it's okay to make mistakes. We learn from mistakes. We improve. Okay, it's how you respond to those mistakes. Some people call them, failures. I just tell them, setbacks and challenges. It's how you respond to all of that stuff. So I like to keep it interesting. So I decided today I'm going with this full screen mode. I've never done it before, so hey, let's see how that goes. Okay, so switching over to the course notes. We're going to be talking about how we draw structures for molecular compounds. And what is a molecular compound? Oh, that blue, science blue. All right, molecular compounds. Molecular compounds are basically held together, the atoms, or in a molecular compound, the atoms are bonded together by covalent bonds. Okay, so by this stage in the course, we'll have talked about the difference between ionic and covalent bonding. We will learn in that process that basically it's not black or white. Bonding is basically a whole lot of gray. At one extreme, we can talk about ionic bonding, which is based on the attraction between ions of opposite charge. In covalent bonding, at the other extreme, we talk about the sharing of electron pairs. But the reality is, any given bond is somewhere between being 100% ionic and 100% covalent. And molecular compound, we're closer to the situation in which the bonding between atoms in the compound is covalent. All right, but within chemistry, we want to understand everything at the atomic and molecular level. The properties of water. We want to be able to understand about thinking about water molecules, their shapes, how they interact, what that will mean for the properties of water versus some other substance. Or thinking about reactions, thinking about why things react in a certain way. Where is the site of attack going to be when two reacting molecules come together? Everything is about molecular structure. So in essence, we cannot understand the physical and chemical properties of matter if we are not proficient in drawing molecular structures. That is the symbolism that is right at the heart of chemistry. It's the symbols that we use. Math has their own set of symbols that they use for representing complex ideas. Chemistry, we have a whole symbolism based on molecular structures. This has to become second nature, I know you will have learned rules for drawing molecular structures in your high school courses. It baffles me to see some of the mental gymnastics that students will go through to draw a structure. They draw structures in which they are representing electrons through some combination of dots, circles that are filled in or not filled in, crosses, triangles, whatever, squares. No self-respecting chemist draws structures for molecules with anything but lines and dots. So the approach that we advocate for drawing molecular structures is what I call a bucket approach. We think of how many electrons we need for describing the bonding in the molecule, and we imagine having them in a bucket. Once we've made a decision about what atom is connected to what atom, in other words, the connectivity of the atoms, we think about taking electrons from our bucket and sprinkling them around the various atoms until we run out of electrons. And we want that distribution of electrons from our bucket just to make sense, to represent the best we can do for representing that structure. We really don't care when we're going through this process of keeping track of which electron started where and where it ends up. Okay? So we don't need hollow circles, filled-in circles, squares, diamonds, crosses, or whatever other favorite shape you might have. Okay? We just need to know how many electrons that we have. So basically, we start from, well, let's decide how many electrons we are dealing with, and from that, we use the group numbers. Okay? And what's going to be relevant for today's class is knowing the group numbers for the atoms, carbon, nitrogen, oxygen. We'll complete the second row, at least of the atoms that form bonds. Why don't you just complete the second row? Put neon in there. What's the group number for carbon? Anybody? 14. Okay, we follow IUPAC, the International Union of Pure Applied Chemistry. The groups are numbered right from left to right, starting from 1. By the time you get to carbon, it's going to be group 14. Nitrogen is 15, 16 for oxygen, 17 for fluorine, and 18 for neon. So what does that tell us about the number of valence electrons that a neutral atom, an isolated neutral atom of this type, will have? The number of valence electrons, so the number of electrons in the outermost electronic shell. What's the number of electrons in the valence shell of carbon? 4, 5, 6, 7, and 8. Okay, so for these group numbers that once we start at group 13, which starts the P block of the periodic table, which we'll have talked about by this point, it's the second digit in the group number that tells us the number of valence electrons in the P block, so 4, 5, 6, 7, and 8. So the group number will tell us how many valence electrons each atom brings to the molecule. Okay, then what we're going to do is we're going to put a pair of electrons between each pair of bonded atoms. Okay, within even the simplest bonding theory, when we're talking about covalent bond, we think of a bond as being associated with the sharing of an electron pair. Okay, a single bond corresponds to the sharing of a one electron pair. Okay, but as I mentioned, every self-respecting chemist, if we're talking about bonding electrons, will represent them in a specific way. And so the way we represent bonding electrons is through a single line that represents a pair of bonding electrons. Okay? A non-bonding pair of electrons, or sometimes we call them a lone pair, is represented with a pair of dots. There's nothing in there with hollow circles, squares, diamonds, crosses, or whatever. Okay? That's what we represent. For those of you that go on to take more chemistry, you will learn about how we extend this symbolism to represent the three-dimensional shapes of molecules using wedge bonds that can be solid or hashed. Oh, it gets all very exciting. I'm sure you can't wait. You will see some of that in Chem 120 when we get to the module that focuses on molecular shapes and then the properties that result from certain molecular shapes. Okay? All right. So there we go. Now, once we've at least accounted for electron pairs bonding specific pairs of atoms together, there's going to likely be extra electrons still left in our bucket. Okay, so then we have to think about distributing those electrons around the atoms to make a sensible structure. And there are some guidelines that we use. So we distribute the remaining electrons that we have in our bucket, okay, according to the following rules. A hydrogen atom typically is never going to have more than, well, will never have more than 2 electrons around it. Okay, so there's a consequence there. Hydrogen is always what we call a terminal atom. Almost everything we say, don't quote me on this, but a lot of what we say in chemistry is a bit of a lie because there's no absolute things. As far as you need to know, hydrogen's never going to be bonded to more than one other thing. Okay, because it can only have 2 electrons around it, it comes from the first period of the periodic table, so its valence shell can only accommodate a maximum of 2 electrons, so that means it can form no more than 1 bond. If you can only form 1 bond, you're always hanging on to something, only one thing. You're always at the end. You're a terminal atom. For those of you that go on, you'll find that hydrogens can actually bridge to 2 other things. Those are a little bit more exotic. You will never encounter that sort of stuff. Well, you won't encounter it in first year. If you go on, you'll see that hydrogen doesn't necessarily have to be a terminal atom. But these are things, if you're drawing structures, it's a good thing to know that hydrogen's always going to be a terminal atom. One of the other things you really need to keep in mind is that elements from the second row. Now we're talking about, these rules describe bonding involving elements from the P block. So those are elements from groups basically 13 to 18, but really focusing on groups 14 to 18. Okay, we have different sets of rules for other parts of the periodic table. I'm not going to get into that. So these rules really apply for the bonding involving P block elements. Within that restriction, there are some other guidelines. You will never, and should never do this, chemistry instructors, I mean, they have eagle eyes for this kind of stuff. You draw a structure that puts more than 8 electrons around carbon, nitrogen, oxygen, or fluorine. They can see that from a mile away. They can smell it. They might even stop marking what you're doing at that point and just say 0. They don't like it. That's like the cardinal sin of chemistry. Okay? Don't do it. And they almost never have incomplete octets. Okay, so they never have more than 8, and they almost never have less than 8. So make sure you always got to do your best to give these atoms, carbon, nitrogen, oxygen, and fluorine, a complete octet when you're drawing your structure. So an octet means 8 electrons. Atoms from the 3rd period and beyond can have expanded octets. So you have to allow for that, or at least be open to the possibility. Where you kind of see this fairly frequently is especially with atoms like phosphorus, sulfur, chlorine, bromine, and iodine. These are elements that we frequently see in structures will have, where the best structure we can draw will actually put an expanded octet around those atoms. Okay. All right, so there's some guidelines. One of the other things that we talk about in drawing structures, we call them Lewis structures, because basically a Lewis structure consists of Lewis symbols for the various atoms with electrons around them, showing the connectivity and the distribution of electrons around those atoms. So a Lewis structure is a collection of Lewis. So a Lewis structure for a molecule is a collection of Lewis symbols connected in a certain way. But we will see examples, starting in a second, where we can draw more than one plausible structure for a molecule. And we have to make decisions, well, given the fact I can draw these different possibilities, which one is best? And for doing that, chemists use the concept of formal charge to make decisions about that. How many of you have heard of the concept of formal charge in high school? Okay, a fair number, not all. Formal charge is very important, okay, for assessing structures. There's a definition that's given here, okay? It's a mathematical definition. I don't use the mathematical definition. I use a conceptual approach. The formal charge is the charge an atom would have when we look at an atom in a structure and we split the electrons in its bonds equally between the bonded atoms, and then we compare the number of electrons around that atom in that situation to the number of valence electron a non-bonded atom of that type would have. Okay? And then we just ask ourselves, has that atom formally acquired or formally lost electrons? And then we make a decision based on that answer to that question, what charge we would assign it. It's a formality, it's a formalism for trying to decide whether an atom, in forming bonds with the atoms around it, has it acquired or lost electrons. The separation of charge generally to create, from neutral species to create separation of charge generally takes energy. And so what we like to do when we draw our structures is to focus on the structure that gives us the lowest formal charges on the atoms. Okay? So that's the guideline. Okay, all else being equal, the most important structure that we can draw, the best structure we can draw, is the one with the smallest formal charges. But given that we can draw a whole bunch of structures, should we dismiss all of the other ones except for the one with the lowest formal charges? And the answer is absolutely not. So when we draw more than one structure, we can think of the true structure as being some weighted average of the possibilities we can come up with. Now, what we would be able to do using this formal charge concept is be able to rank various structures in terms of their importance or their weight. The one we give the highest weight is going to be the one with the smallest formal charges. Other ones that violate other guidelines we have or impart large formal charges on the atoms would carry lower weight. But the true structure, we would say, is a weighted average of these possibilities, and that the true structure is a hybrid, or just a fancy way, a mixture of a weighted average of the structures we can draw. But a resonance structure does have some other very important meaning as well. And in order to emphasize that, I do want to focus for a moment on the distinction between what are called isomeric structures and resonance structures. And the difference is quite simple. When we're looking at two different structures that have the same molecular formula, if the two structures differ in the spatial arrangement of the atoms, then we're talking about isomeric structures. So isomeric structures have different spatial arrangements of atoms. Okay? To convert from one isomer to another, we would have to change the spatial arrangement of the atoms. In other words, we'd have to break certain bonds, rearrange things, and form new bonds. Okay, that takes energy. Isomers are chemically distinct compounds with their own properties. They behave differently, and we have to chemically convert one into the other, generally speaking. Resonance structures, on the other hand, differ only in the distribution of electrons. There's the same spatial arrangement of atoms, but different distribution of electrons around those atoms. Okay, so to emphasize that, resonance structures have a different distribution of electrons, but the same spatial arrangement of the atoms. We can use a very simple molecule to illustrate the difference. I am pretty sure that if I asked you guys to draw the structure of carbon dioxide, or something, I wouldn't say name it, draw the structure for the compound that has the formula CO2, invariably everyone would draw what is identified as structure 1 here in the course notes, which has carbon as a central atom, which is then doubly bonded to two oxygen atoms. Okay? Well, somebody with a bit of imagination and creativity, I'm just trying to be a wise ass, might draw structure 2. You'll notice that structure 2 has the same formula, the same total number of electrons around the atoms. Okay? How do we know? Well, because the number of valence electrons is going to be equal to 4 from carbon plus 2 times 6 from oxygen. Okay, we would end up with 12, that's 16. How do I go back to black? I'm not sure. I'll figure these things out later. Okay, so we're at 16. You can see 2, 4, 6, 8, 10, 12, 14, 16 electrons in both cases. Okay, but you will notice the difference between these two structures is a different spatial arrangement, a different connectivity of the atoms. So we would call these isomeric structures. Structures 1 and 2 here are isomeric. Okay. If you look, there's some charges given above the carbon atoms here, above the carbon and central oxygen atom in structure 2. How do we get that? Well, let's think about the carbon atom. The carbon atom is surrounded by 2 lone pairs, 2 non-bonding pairs, and two bonding pairs. So this carbon atom in this structure owns 4 electrons from the 2 non-bonding pairs plus half of the 4 from the 2 bonding pairs, right? There's 2 bonding pairs. Each of those lines represents a pair of electrons. In this formalism of assigning formal charge, we think of the electron pairs as being shared equally between the 2 atoms. That's, again, not quite true, but for this formalism, this is what we do. So we would say 4 plus a half of 4, so that's 4 plus 2, is equal to 6. Compared to a non-bonded carbon atom, an isolated non-bonded carbon atom, we've said a non-bonded carbon atom has 4 valence electrons. In this structure, it owns 6. It has formally acquired 2 electrons. If we said something gained 2 electrons, it's going to gain a charge, or it's going to acquire a charge of -2. Okay? These kinds of calculations you can do in your head. You don't need to apply formulas. And if you want to get good at this kind of thing and be what I call proficient, a self-respecting chemist, and I know you're not, probably the majority of you are not in a chemistry program, but I'll tell you, when we teach chemistry, you're part of the chemistry community at that point. You're taking chemistry, probably not by choice, but because your program says you need to take it. And so the people who have designed your program feel that you need to know a certain amount of chemistry. And so for all intents and purposes, we're all chemists when we're in the chemistry classroom. Okay? So these kinds of calculations, these thought processes are best done, thinking conceptually about it rather than applying formulas, because it means you understand what's going on. If you think about this central oxygen atom, the central oxygen atom owns 1/2 of 8 electrons. There's 4 bonding pairs, so that's 8 electrons. They're bonding pairs, but 1/2 of 8 is equal to 4. But oxygen is from group 16, so that means a non-bonded isolated oxygen atom would have 6 valence electrons. But in this structure, oxygen owns only 4. It has formally lost 2 electrons, so we assign it a formal charge of +2. you will notice that the sum of the formal charges will equal the total charge on the molecule. I'm not going to go through the process, but the formal charge on oxygen, the terminal oxygen atom in structure 2 is 0. In structure 1, all the formal charges are all 0. So going back to this formal charge concept, structure 1, all the atoms have formal charges of 0. So comparing structure 1 and structure 2, we like structure 1 better than structure 2 because the formal charges are smaller in that structure. So in determining, which bonding arrangement is more likely for a compound with the formula CO2, it's going to be structure 1. Okay, but those structures 1 and 2 are not what we call resonance structures, but isomeric structures. Okay, it should be no surprise that the formal charges always add up to the total charge on the species we're talking about, because the assignment of formal charges is a formalism. Any formalism that breaks the rule that charges should add up to the total is a ridiculous formalism. Okay, so that's a way that we know that our assignment of formal charges is correct, because they better add up to the total charge as well. Okay, so now if we focus on structure 1, where we have carbon as the central atom, we can draw more than one distribution of electrons around the atoms. So now in the second set of structures, now we're talking about resonance structures for the isomer 1, so carbon with the central atom. Structure A, that is shown here, is is identical to structure 1 above. But now focusing on that spatial arrangement of atoms, we can distribute the electrons in a different way. In order to go from structure A to structure B, we are not going to move any atoms. We're going to keep the same spatial arrangement. We can move the electrons around. And we can represent the movement of electrons using another symbolism, very popular in chemistry and used frequently, to show that we can, okay, so what are we going to do? We're going to move this guy out. So we're going to move one bonding pair out from the carbon and the oxygen on the right side. Now, we know that carbon needs to have a complete octet. That's part of one of the cardinal rules of these drawing structures. So if we're going to move a bonding pair out from around carbon, we're going to have to move something else in to replace or offset what we've just done. And so we can represent this rearrangement or redistribution of electron pairs using curly arrows. Okay? Rick, for years, has taught organic chemistry, tutored students in organic chemistry, helped me write the organic chemistry chapters in a textbook. Do we use curvy red arrows all the time in organic chemistry?
That is the language.
That is the language and the symbolism that is in organic chemistry. Many of you, if you're in a life sciences program like biology, biochemistry, biomedical sciences, chemistry, and even materials and nanosciences, you will take organic chemistry in second year. We introduce you to these ideas so that you can build on your knowledge and be ready for organic chemistry in second year. Okay? And we expect that you can take that with you. Okay? It's not just about remembering it long enough to do well on the next quiz, test, or exam. It's about understanding it so that you can take it with you as you move along through the program. Okay, so in that case, what we end up with is structure B, which has now a triple bond between the oxygen on the left-hand side and carbon, and a single bond between carbon and the other oxygen. Okay? The formal charges are shown. You can go through the arithmetic. I'm not going to focus too much on those, but you make sure you can assign these formal charges yourself. And then by another arrangement or distribution, redistribution of electron pairs. I won't show it using red arrows, but there was nothing special about putting the triple bond between oxygen on the left and the central carbon. We could have put the triple bond between the carbon and the oxygen on the right, okay? So, thinking back to that original question we had, there were some statements about resonance structures. There were statements about isomeric structures. So we've covered off the difference between those. Another word, and the formal charges appeared in there, and so we've dealt with formal charges. Another word that came in there was non-equivalent, which implies there's also the issue of equivalence. So thinking about these three structures, A, B, and C, which structures are equivalent or non-equivalent? Who would like to venture a guess? And it's okay, feel safe. Yeah? B and C are equivalent. That's what you said? How many people would agree with that statement that B and C are equivalent structures? That's good. They are equivalent structures. How did you make that decision? Somebody, and anyone else want to answer? Yeah. It's one way to think about it if you flipped it in space, but we don't want to think about actually flipping it in space because that opens up a whole other area of chemistry that's not quite related to this, but I like where you're going with that. Yeah?
Because there's carbon-free oxygen, one oxygen in both cases.
Right, we have, so let me paraphrase what you've said. I like your answer, so that's good, but I'm going to just repeat it so everyone can hear. B and C both have one carbon oxygen triple bond, one carbon oxygen single bond. The distribution of formal charges is the same, meaning that we have a +1 formal charge on the triply bonded oxygen, a -1 formal charge on the singly bonded oxygen, so that there's really nothing to distinguish them. They're equivalent. What does that mean? That means if we think of the true structure of CO2 as being a weighted average of structures A, B, and C, structures B and C would carry the same weight. Now, structure A and B, for example, are non-equivalent because they have a different distribution of bonds. Now we have two carbon-oxygen double bonds instead of a single and a triple. Formal charges are different, so A and B are non-equivalent resonance structures. And based on the formalism that the formal charges, or the structure with the lowest formal charges are best, okay, we would pick structure A to be the most important or carry the highest weight in the weighted average that contributes to this. And this concept of a weighted average, that the true structure is a weighted average of the reasonable possibilities, is important. Because as we move along through chemistry and we start to think about representing these structures within a quantum mechanical sense, okay, we would return to this idea of weighted averages of the possibilities describing, or the quantum mechanical description for each of these possibilities. Okay, I don't think I want to say anything else about that. The other convention we follow is we typically only show non-zero formal charges. Okay, just simplifies the clutter, or eliminates the clutter of showing zero. So in these cases where a formal charge isn't shown, the formal charge is actually zero. Make sure you can verify that yourself. All right, well, these are pretty simple examples, and who thought we could cover all of the topics that was mentioned in that problem and apply to much more complicated molecules in something so simple as CO2? And that's why chemistry is a beautiful thing, and that's why you will all wish you were in chemistry in the long run. But follow your misguided paths to wherever you're going, and just teasing, of course. Yeah, so let's look at an example. I'm not going to go through all of these, obviously, but let's focus on one of these. So we're just going to go with A. So typically, in my lecture, you have your course notes with you. We try to focus as much as we can on problem solving, applying the concepts. Rick mentioned it. I like to talk. So, there are things that happen that lead up to solving problems, and sometimes I just get way off base. But, eventually we do solve problems. And this is what we're going to do now. So for HOCN, first step, number of valence electrons. So the number of valence electrons is going to be 1 from hydrogen. Hydrogen, I left off of this. Hydrogen is way over in group 1. There's 12 columns between hydrogen and the rest, this group. But hydrogen's in group 1, so we have 1 valence electron from hydrogen, 6 from oxygen, 4 from carbon, and 5 from nitrogen. Okay, so what do we got? We've got 10 plus 6, so that's 16 electrons to deal with. And these are valence electrons, and that's what we use for describing bonding, are the electrons in the valence shell, the outermost shell. The electrons furthest from the nucleus, are the ones that are going to be most likely to interact with another nucleus, okay, to form bonds between the nuclei of different atoms. Okay, so let's just start. So we've done step 1. This is not really an algorithm, but it's a process through practice you get good at. Next part of it is to put a pair of electrons between each pair of bonded atoms. And the reason we wrote the formula this way, HOCN, is we want you to focus on that bonding arrangement. Okay? And typically that will be the examples that we want to focus on. We're interested in describing the bonding for a particular arrangement, spatial arrangement of the atoms, and we want you to come up with the most sensible distribution of electrons around the atoms in that spatial arrangement. So at this point, I've drawn a structure that includes 2, 4, 6 electrons. I've got 10 more to go. Now, I'm not the smartest person in the world, not the quickest bunny in the forest, not the sharpest knife in the drawer. So, I might just say, I remember this rule, we should complete the octets of the atoms like O, C, and N. So I've got 10 more electrons, so you know what I'm going to do? I'm kind of tired today, I don't want to think anymore, so I'm just going to start filling in the octets, completing the octets of the atoms left to right. So I've got 2, 4, 6 accounted for, 8, 10, 12, 14, 16. So all I did there was just take from my bucket of electrons, start completing the octets of O, C, and N, just left to right. Well, you know what? I haven't violated any rules. But I should assess what I've done. Well, the technical assessment here, the technical assessment of this structure is yuck. What's wrong with it? Now over here.
Just found out there's too many electrons around the carbon atom.
Well, there's 8 electrons around there. What do you mean by? Can you be a bit more specific? Because I know what you're getting at.
Generally, there are 4 valence electrons for it, and
Okay.
just having 4 extra and having about
Okay.
having quite a bit less.
So it's got 8 electrons, but not so that the formal charge is small, right? It's formally acquired electrons is another way of saying, I think, what you're after. Anything else? Yeah? And N, the nitrogen atom, has an incomplete octet. Okay, so if I was to assign formal charges here, the formal charges on hydrogen, 0. It's a terminal atom. Hydrogen owns half of that bonding pair. Half of 2 is 1. Well, an unbonded hydrogen atom owns 1 valence electron. Okay, so it has neither formally gained nor lost any electrons, you get used to the idea that when hydrogen is a terminal atom, its formal charge is always going to be 0 when it's got just one bond around it. This oxygen, with practice, you start to recognize an oxygen with 2 lone pairs and 2 bonding pairs as having a formal charge of 0 as well, because that oxygen owns the 2 non-bonding pairs, so that's 4 electrons, plus half of the bonding pairs, so that's a half of 4. So 4 plus a half of 4 is 6, which equals the number of valence electrons in a non-bonded oxygen atom. And so it has neither formally gained nor lost any electrons. But carbon, on the other hand, owns 6 electrons in this structure. The 4 non-bonding electrons, and then half of the bonding electrons, so 6, just like the oxygen we talked about. But 6 is 2 more than the 4 a non-bonded or isolated neutral carbon atom would have. So it's acquired 2 electrons, has a formal charge of -2. Without going through the arithmetic, I can deduce that this nitrogen must have a formal charge of +2, because I know the formal charges have to add up to 0 because HOCN has no charge. But you could go through the arithmetic like we did. So this structure is no good from the point of view that nitrogen has an incomplete octet. And the formal charges on C and N are kind of high. Okay. When we're drawing structures, we really don't want to be creating formal charges with magnitudes larger than 1. Sometimes we can't get away from it. There will be atoms that carry a formal charge of +1 or -1, and that's okay. I mean, as far as formal charges go, that's okay. But when we start getting up to +2 and -2, +3 and -3, that's your first signal. You got to do better. Okay. Well, given that we are in a situation where we don't have enough electrons around nitrogen, we got to think about it distributing the electrons in a different way so that we get more electrons around nitrogen and less electrons owned by carbon so that we can reduce its formal charge as well. Okay, so the simple thing to do is to move some electrons that are currently non-bonding on carbon into the bonding region between carbon and nitrogen. Okay? So we're going to draw another structure. And to emphasize that these structures are connected in the sense that we're talking about the same bonding sequence, but a different distribution of electrons to describe that bonding sequence, we use a double-headed arrow. Okay? This does not mean that we're talking about a reaction or that these structures oscillate back and forth from one to the other. That has nothing to do with what it means. It is a symbolism that just says that these two structures are connected in the sense that we're talking about the same spatial arrangement of atoms with a different arrangement of electrons around them. Okay? And things on either side of this double-headed arrow are technically what we call resonance structures. So once we do this redistribution, we end up with a carbon-nitrogen triple bond. Okay, so you will notice, now I'm using lines rather than dots to do all of this. Okay, if I go through this assignment of formal charges, it's going to be 0. Nothing has changed around hydrogen or oxygen, so the formal charges won't change. If I focus on carbon, carbon owns half of those 8 bonding electrons. Half of 8 is 4. Well, 4 is exactly equal to the number of valence electrons in a non-bonded neutral carbon atom. So carbon has neither formally gained nor formally lost any electrons, so it has no formal charge. Nitrogen owns half of the 6 bonding electrons, so half of 6 is 3, plus the non-bonding electrons, so 3 plus 2 is 5. 5 is equal to the number of valence electrons in a non-bonded neutral nitrogen atom, so a formal charge of 0. I went through the arithmetic that time, but I could have deduced that also by just knowing that the sum of the formal charges had to add up to 0. I like doing it for each one so that then I can check at the end that they do add up to 0 as a way of checking that I've done things properly. If I made a mistake on hydrogen, oxygen, or carbon, and then just said, well, I'm going to deduce the formal charge on nitrogen by invoking that rule that the sum of the formal charges has to equal the total charge. If I made a mistake along the way, that mistake will be propagated into assigning the formal charge on nitrogen as well. Well, this is not the only structure. What we can do is turn a non-bonding pair around oxygen into a bonding pair. We will end up with a double bond between carbon and oxygen. Okay, but if I'm going to put more electrons around carbon, if I stopped and I just continued drawing what I did in the previous structure, in other words, with a carbon-nitrogen triple bond, I would commit the cardinal sin of chemistry, and that would be to have 5 bonds around carbon or 10 electrons around carbon. Okay, so if I'm going to put something in around carbon, I'm going to have to take something else out. Okay, and so, whoops. So I'll end up with 2 non-bonding pairs around nitrogen. If I assign the formal charges 0, it's going to be plus 1, 0, 1, 2, 3, 4, 5, 6. So here we go, minus 1. Now, one of the tricks I teach my students in being able to count electrons around an atom, in the sense of how many does that atom own, is to count dots and lines. All right? So if you look at the nitrogen, if I just count dots and lines, I have 4 dots and 2 lines. That turns out to be, that number of dots and lines is exactly equal to the number of electrons owned by nitrogen. Okay, because in this formalism, a line, the nitrogen only owns half of that pair. Okay, so you can actually get quite good or quick at this by counting electrons, by just counting or how many electrons an atom owns by counting dots and lines. So that's kind of a little tip or trick. You still have to remember that a line represents a pair of electrons, but by just quickly counting up dots and lines, this will always also equal the number of electrons that's owned. Okay? It's kind of a neat little mathematical consequence of the formalism, but that's exactly what I did when I was looking at nitrogen. I just counted dots and lines. I came up with the number 6. I compared 6 to 5. Hey, that's an extra electron. Formal charge minus 1. All right. Well, we could have done the same, do this again with moving in a non-bonding pair of electrons on oxygen, moving out a non-bonding pair of electrons, or bonding pair of electrons between carbon and nitrogen as non-bonding. So we would end up now with an oxygen-carbon triple bond, a carbon-nitrogen single bond, and 3 lone or non-bonding pairs around nitrogen. The formal charges here now, 0. Nothing's changing around hydrogen. Oxygen, if I count the number of lines here, there's 4 lines. That 4 lines, okay, is 4 lines. We're calling it 4 lines. The number of electrons owned by oxygen is half of the 8 electrons represented by those lines. Half of 8 is 4, which happens to equal the number of lines. This is why this little trick works. So 4 is 2 less than the 6. so that's a formal charge of +2. Carbon is 0, and then this nitrogen has 2, 4, 6 non-bonding electrons, so 6 dots and a line, so that's 7. Okay, 7 is 2 more than the 5, that's a -2. So if I call these structures 1, 2, and 3, are these structures 1, 2, and 3 equivalent or non-equivalent? Yes. You believe correctly. Well, you can believe whatever you want, but your belief is correct. They are non-equivalent, right? We have different numbers of, where the triple bond is located between which pair of atoms, different distribution of formal charges. So they're non-equivalent. 1, 2, and 3 are non-equivalent resonance structures. Which one's the best? If we had to draw a single structure, the one that was most representative, the one that would carry the highest weight in representing this structure, which one is it? How many say structure 1? How many say structure 2? How many say structure 3? Okay, good. Structure 1, the ones have it, and structure 1 is the best. So when we say the most important, we mean the best. Or we mean most representative of the true structure. That's not even good spelling. Representative. Okay? And why do we care about all of this? Being able to draw one structure? Well, because the reality is electrons are indistinguishable. An electron in this molecule is simultaneously interacting with every nucleus in that molecule. It's not restricted. It may have originally resided on a carbon atom, but you know what? At the end of the day, once it's in the molecule, once this molecule has been formed by whatever means, it is going to be interacting with all things simultaneously. Yeah? If we were going to rank them in terms of energy, so the question was, does the best mean the most stable? Generally speaking, I don't know if I want to, die on that hill defending that particular statement, but I would say, generally speaking, that would be the case, that would represent the most stable structure. But the reality is, because of this complication, that electrons are indistinguishable. If we let this molecule form, we have no right to be able to say which electron belongs to which atom at that particular point. All of the electrons are interacting with all of the nuclei. And especially, anyway, I'm just going to leave it at that, okay? But that's not a bad way of thinking about it. All right, so way I would like to wrap up, holy mackerel, I could go all day. Who wants to do chemistry all day? All right, we got four people. All right, let's wrap up. What are we going to wrap up with? We're going to wrap up with this question. Let's get ourselves a clear slate here. You know the drill. The timer's going. I'll give you 2 minutes now. You talked about this problem. Now you hopefully have learned something. So we're good on the time? Okay, guys, I'm going to give you to the 1 minute mark. So when this thing gets down to the 1 minute mark, which is about just over 30 seconds, please have your answers in by then if you're going to answer, just so that we can wrap this up and move on to the next part. Okay, so I'm going to wrap this up. I'll give you 5 more seconds. 4, 3, 2, 1. How do we do? Okay, so there was a significant improvement in learning, and I actually give you guys credit because I didn't talk about everything that would help you to select the correct answer in this case, though most of you have ended up there at 92%. That was in the 70s before, so you know it's good. You come to class, if you pay attention, you interact, you ask questions, you answer questions, you can learn something. But the first key to success is just showing up. Okay, and I mean showing up and being there, not, you know, on your phones and your devices, you know, checking out my Facebook page and stuff like that. But I do want to, before I wrap up, I do want to address something. Between structures 1 and 2, and we're going to assign some formal charges here. The formal charges on nitrogen, +1 and -1, and in structure 3, it's going to be -1 and +1. Okay, so one of the issues I didn't talk about, in this particular case, comparing structures 2 and 3, okay, they're resonance structures, same distribution of atoms, same spatial arrangement of atoms, but a different distribution of electrons. Why would you prefer or say that structure 2 is better than structure 3? Why is structure 2 better than structure 3? I didn't address this concept. Up there, yeah? It has to do with what atom the charge is on it, but it's not because it's outer. Yeah. Oxygen is a more electronegative atom. I like that answer. Who wants to tell me what electronegative means? Yeah, here. A measure of an atom's ability to attract electrons towards itself. So oxygen, is oxygen the most electronegative element in the periodic table? No, which one is? Fluorine, but oxygen's second. Right? So in deciding between structures 2 and 3, we're putting the negative formal charge on the atom that has the higher electronegativity, the strongest tendency to draw electron density towards itself. So the distribution of formal charges in structure 2 best represents what we know about oxygen. You see, even when you think something is done, there's always more to learn. And that's how I love to end my classes, to keep your interest piqued so that the next time you can come back and say, there's more to this story, where are we going to go? So finally, that's it for me. I'll stick around to interact with some of you guys after, during lunch, but I'd like to, at this point, I'm turning it back to Rick. So I'm going to turn it back to Rick. So enjoy the rest of your day.